In this video, we will continue to look at applications of enolates, and we're going to start looking at alkylation of enolates. And we're actually doing it out of order, so we're going to look first of all at direct alkylation of enolates. In Chapter 11, we looked at some general examples of nucleophilic substitution, so that if we have a nucleophile, this can share its electrons with an R group, pushing away a halogen or some other leaving group, giving us a new bond between the nucleophile and a carbon and pushing out a leaving group. We've seen a variety of nucleophiles that can be used, and we also talked about substitution versus elimination. So we know that SN2 substitution works best with methyl and primary alkyl halides. With secondary alkyl halides, there is competition between substitution and elimination. And with tertiary alkyl halides, elimination is a big issue. Well, now let's try to determine whether we can carry out nucleophilic substitution using an enolate as the nucleophile. So if we start out with acetone, for example, and we treat this with base so that it pulls off one of the alpha protons, then this enolate will be generated. Well, can this enolate act as a nucleophile? If so, it could share its electrons here, pushing away bromine as the leaving group. So we would get this with a new bond to the methyl group that used to be connected to the bromine. So the good news with this reaction is that because our nucleophile is a carbon, then we are making a carbon-carbon bond, so that's a good thing. But the bad news is there are a number of competing reactions, and so there are some issues with selectivity. So let's look at a few other examples. If we have an aldehyde and we treat it with hydroxide, then this can grab off a proton, and we are going to have some of this enolate. And it's possible for this enolate to react with the methyl bromide so that these electrons add here, pushing away bromine as a leaving group, and that would lead to some of this. But keep in mind, because of the base that we're using and the pKa values, then at equilibrium we know that we have some of our enolate, but we have lots of our aldehyde. So a competing reaction, one that we're going to talk about in the next chapter, is rather than doing nucleophilic substitution, this enolate can do nucleophilic addition, adding to the carbonyl of the aldehyde, pushing these electrons up onto here, and so this will be competition. If we have a ketone and we treat it with hydroxide followed by methyl bromide, and we're trying to do nucleophilic substitution, well, this can grab off one of these protons, giving us this enolate, which can then react with the methyl bromide, kicking this out, giving some of this. Now in this case, once again, the position of equilibrium between the ketone and the enolate lies toward the ketone, But if you remember, when we talked about nucleophilic addition, we saw that nucleophilic addition to a ketone is slow and the equilibrium is not favorable. So we don't really have to worry about nucleophilic addition competing with nucleophilic substitution the way that we would in the example above. But there's a different complication because this particular ketone is not symmetric. So I showed the base grabbing off a hydrogen from one of the alpha positions. Well, it's also possible for the base to grab off a proton from the other alpha position, and that would lead to this product. So we would make some of this ketone and some of this ketone. And a third example, if we started out with an ester, well, we would want to be sure that we treated it with an alkoxide that matches the alcohol part of the ester. But if this formed some of the enolate, we would have this. And then it's possible that this could react with the methyl bromide, pushing away bromine as the leaving group, and that would give us some of this product. But once again, think about the position of equilibrium, and using methoxide, we're going to have a small amount of enolate and lots of ester, and so this can do nucleophilic acyl substitution, which is another reaction that we're going to talk about in the next chapter. So while it's possible to generate an enolate and have that act as a nucleophile in a nucleophilic substitution reaction, there are definitely some limitations. The examples that we've shown here, these aren't going to work very well, but there are ways that each of these could be optimized. One of the ways to address some of the issues that come up with using hydroxide or an alkoxide, namely having a reaction between the enolate and the aldehyde itself, for example, is instead use a much stronger base such as LDA. So in this case, the position of equilibrium between the ketone and the enolate lies very far toward the enolate. Same thing with an ester or a nitrile, for example. So if we start out with acetone and we treat it with LDA, we should be able to make plenty of this enolate. And then if we add in the ethyl iodide, then this enolate will act as a nucleophile, share its electrons with this carbon, pushing away the iodide as a leaving group, giving us some of this product. So it is possible to do a direct alkylation of enolates, especially when LDA is used to form the enolate. This approach is also useful with esters. So if this ester is treated with LDA, then we're going to generate, first of all, some of this enolate. And then this enolate can react with the propyl bromide, share its electrons with the carbon, push away bromine as a leaving group, leading to this product. Oops. Leading to that alkylation product. Notice one way of thinking about the reaction is that here is our nucleophile and here is our Rx, and we are doing nucleophilic substitution leading to this product where this came from the nucleophile and this came from the alkyl halide. But another way of thinking about this is if we focus on the ester from which we form the ester enolate. Now this is the ester enolate, which now has an alkyl group attached. And so that's why we refer to this as an alkylation of an enolate. A nitrile can also be alkylated, so treatment with LDA will give this enolate, and then adding in the alkyl halide. This will share its electrons here, push away bromine as a leaving group to give this product. In our next example, we have a ketone, but unlike what we had up here, in this case, this ketone is unsymmetric. So we do run the risk of forming an enolate at this position and forming an enolate at this position. When we're using LDA, because this is so bulky, it will be a little bit hard for it to grab off this proton where it's more crowded. So instead, it will primarily pull off one of these protons. And so that means we will get mostly this enolate, and then that can react with the ethyl bromide to give this product. If we look at our last example, here we have a beta diketone, and keep in mind that the pKa value of these hydrogens is about 9, so this means we can use a much milder base to generate the enolate here. Even with a milder base, the position of equilibrium will lie very far toward the enolate. So, treatment with potassium carbonate can give us some of this enolate, which can react with the methyl bromide, pushing away bromine as a leaving group, giving us this product. So we can see that direct alkylation of enolates does work, but there are limitations. These reactions work best when you have a beta diketone or some other beta dicarbonyl. You can use a mild base to generate plenty of the enolate, which can then carry out nucleophilic substitution. For other ketones, it works best using a strong base such as LDA, but it still works best when you are using a symmetric ketone. Having a bulky base can maximize the formation of the enolate from this position rather than this one being more crowded, but still there's going to be a risk of a mixture. Esters, nitriles, these can be alkylated, again using LDA. With aldehydes, it can work, but there are other types of competing reactions that would also possibly get in the way. So direct alkylation of enolates is a possibility. In our next videos, we're going to see a couple of different approaches to alkylate enolates.